So in Chapter 4, with a few exceptions, virtually all higher order differential equations we solved were linear with constant coefficients. The principal exception to this were Cauchy-Euler equations, but the form of that was very restrictive. In this chapter, we're going to see a method for solving linear higher order differential equations with variable coefficients. Now this method is going to involve power series. So we begin Chapter 6 with a review of power series from calculus. So let's recall from calculus what a power series is. Okay, so with this sort of x minus a here, we would say that this is a power series centered at A. Okay, so as an example, we could have this guy here. We can see that this power series is centered at a equal -1. And the Cn of this power series, which is like the coefficient of the x minus a raised to a power, would be this part here. In this case, 1 over 2 to the n plus 1. So we'd refer to that as the coefficient of the power series. Here's another example. So here we can see this is a power series centered at a equals 0. And that's because it's really of the form x minus 0 to the n. The coefficients here are 1 over n factorial. Hopefully you recognize this guy even. This is the Maclaurin series for the exponential function. So to be clear on the distinction of the terms here, Taylor series, power series, and Maclaurin series, a power series is just any infinite series of this particular form with x raised to a power. A Taylor series is specifically a power series that's identified with a function, and a Maclaurin series is a Taylor series where the center happens to be 0. The distinction between all of these terms isn't especially important for what we're going to be doing here. So, of course, we are only concerned with power series on their intervals of convergence, which are always symmetric about the center. So an interval convergence would have, say, the form a minus r and a plus r, which is an interval centered at A. And r would be the radius of convergence here. Now note that the actual endpoints of the interval may or may not be included. So really, these could be parenthetical or brackets or a mixture of the two. And one more comment here. The radius of convergence can be 0 or infinity. When the radius of convergence is 0, then the corresponding power series will only converge for the single point at the center, which makes that particular power series not very interesting. When r is equal to infinity, then your interval of convergence is all real numbers, and then your power series will converge for every x value. So let's see a few examples where we simply recall the method for determining the radius and interval of convergence for a power series. All right, so let's find the interval of convergence and the radius of convergence for this power series. So the typical way that we do that is via the ratio test. So the ratio test has us evaluating this limit, an plus 1 over an. So an plus 1 over an would be an plus 1, so that would be this thing with all the n's replaced by n plus 1. And we could put that all over an, but in practice it's a lot easier just to multiply by the reciprocal of an, of course. So that would be 5 to the n, rad n in the numerator, and then 2x minus 1 to the n in the denominator. Okay, and let's line everything up with its friends. So we have 2x minus 1 to the n plus 1 over 2x minus 1 to the n. We have 5 to the n over 5 to the n plus 1, and we have rad n over rad n plus 1. So everything will have some sort of a friend that it can line up with because you want to look for some sort of cancellation. Okay, so these 2x minus 1 things, they simply reduce to absolute value of 2x minus 1. And we can close the absolute value all the way around that expression as we have, because the other stuff's naturally positive, right? So that battle of the exponentials becomes simply 1/5, and these guys don't really do anything, except that's okay because they're not going to really impact the limit. In fact, that's the only part where there is an n, and the limit of this algebraic factor is simply 1, which means that this entire evaluation comes out to that. Okay, now if you're rusty on the ratio test, the ratio test basically says you work out this limit, and if you get a quantity that's strictly less than 1, then the original series is absolutely convergent. If you get a quantity that's strictly greater than 1, then the original series is divergent. If you get a quantity that's equal to 1, then the ratio test is inconclusive. So now the context here is that we're not checking to see if a particular series is convergent. We actually have a power series, which depends on x. So it's this series we expect to converge for some x and maybe diverge for other x's. So what we do is we just decree that we have a convergent series, which means that we are going to set this expression here to be less than 1, and we're going to solve for x. Now, as an inequality, this is going to give us an interval as a solution, and well, that interval will be the IOC. Mostly, though, because the endpoints of the interval will still be undetermined. We'll have to worry about that in a minute. So solving for x, we get the absolute value of 2x minus 1 is less than 5. And this tells us that 2x minus 1 is between -5 and +5. So just continue isolating x in the middle. We'll add 1 to both sides, and we'll divide both sides by 2. Okay, so we can see that the IOC is an interval from -2 to 3. But we don't know the delimiter of the interval, meaning we don't know if these are brackets, parentheses, or some mixture. And we'll have to figure that out. The radius of convergence is half of the length of the interval. So you can think of it as b minus a over 2 if you want. In this case, it would be 3 minus -2 over 2. So that would be 5 over 2. Okay, so how do we figure out the endpoints of the interval of convergence? Well, those are specifically the x values for which this expression here evaluates to 1, meaning the ratio test is inconclusive. Like, if we let x equal 3, then we're going to obviously see that this is 6 minus 1 is 5 over 5 is 1, right? And the same if x is -2. So the ratio test is not going to help us get those endpoints. The way we figure that out is we literally let x equal those numbers in the original series and investigate the form of the series. So let's let x be -2. And that means that the series is going to be 2 times -2 which is negative 4 minus 1 is negative 5 to the n over 5 to the n rad n. So the negative 5 to the n over 5 to the n is negative 1 to the n, 1 over rad n. So is this a convergent series? Well, we can use the alternating series test. 1 over rad n is decreasing, and this limit here is equal to 0. So yes, the power series when x is equal to negative 2 is indeed convergent. So negative 2 gets included in the interval of convergence. Now let's let x equal 3 and see what happens. So when x is equal to 3, we get 2 times 3 is 6, 6 minus 1 is 5, so we get 5 to the n over 5 to the n rad n. Of course, those 5 to the n's cancel, and we just get 1 over rad n. So is that series convergent or divergent? Well, it's a p-series, and p is equal to 1/2, so that is a divergent series. What is it about 1/2 from which we can conclude that this is a divergent series? 1/2 is less than or equal to 1. So therefore, 3 is not included in the IOC. So our conclusion is that the IOC includes negative 2, but does not include 3. And the ROC, which we calculated earlier, is 5/2. All right, same kind of issue here. We're going to find the interval of convergence and the radius of convergence for this power series. So, as always, we will start with the ratio test. Okay, so an plus 1 is everything with n replaced by n plus 1. And we're going to divide by an, which is really just multiplying by the reciprocal. Okay, let's line everything up with its friends. Strictly speaking, we can just throw away these negative ones. Let's let them survive one more round. We'll match the factorials with each other. Looks like we're going to have a little bit of a factorial battle to resolve. And we have x to the 2n plus 2 over x to the 2n. So again, the negative ones, they actually algebraically cancel just to be negative 1, but the absolute value annuls the negative 1 altogether, so we can just completely throw them away. The absolute values will collapse only around the x factors, because the factorials are always positive. So we have 2n factorial over, to resolve the factorial battle, we should unwrap the larger one. So 2n plus 2, 1 less than that is 2n plus 1, 1 less than that is 2n. There's our factorial cancellation. And what do we have over here? We're left with x squared. And actually, we didn't even need the absolute values there because x squared is positive. So what do we have? Limit as n approaches infinity of 1 over 2n plus 2, 2n plus 1, and then an x squared. All right, well, for any finite number x that you would plug into this series, as you take n to infinity, you're going to get 0 out of this limit. So this is a situation where we get 0 for all values of x. Now 0 is less than 1, of course, for all x, right? So this means that the interval of convergence is all real numbers. This is the best case scenario with a power series. And in this case, we would also say that the radius of convergence is infinity. This shouldn't be surprising to you if you recognize this particular Maclaurin series. This guy is exactly equal to, and in many cases taken as the definition of cosine of x. And we know that sine, cosine, sinh, cosh, and e to the x have intervals of convergences of all real numbers. Okay, let's do one more interval and radius of convergence problem. And as always, we will start with the ratio test. So n plus 1, that's 2 to the n plus 1, n plus 1 factorial, x to the n plus 1, over an. This time, it's probably a good idea just to write it directly as a fraction. And everything's already lined up with its friend. That's very nice. So we get 2 to the n plus 1 over 2 to the n, which is 2. We have a factorial battle. Of course, unwrapping the larger factorial would be just n plus 1 with the n factorials canceling. And then we have the absolute value of x. Okay, so now let's take this limit as n approaches infinity. Of course, this is going to approach infinity no matter what the value of x is, with one exception, and that is if x is equal to 0, in which case this would evaluate to 0. Okay, so the only situation where the ratio test evaluates to a ratio that is less than 1 would be in the singleton case where x is equal to 0. This means that this series only converges exactly if x equals 0. Okay, so that means that the interval of convergence is the interval starting at 0 and ending at 0, and of course we need brackets here to indicate that we include 0. Now this is a really non-standard way of writing an interval. It's not wrong, but when we're talking about an individual set containing just a few items, including just one item, we would use the set notation here. So that's with braces, and we're just going to list the 0, and there it is. So this means the singleton set 0. The radius of convergence is 0 here. So in the universe of power series, this one is kind of dumb. All right, so now we're going to use known Maclaurin series to find the Maclaurin series for various functions. And of course, you need to be familiar with the main well-known Maclaurin series. So good idea if you've forgotten these particular Maclaurin series, because you may not have seen them since calculus, is to study page 239 of your textbook, which lists all of the really important ones that we use on a regular basis. So yeah, taking a look at this particular function, we can see that the main function involved here is the exponential, e to the x, which of course has some minor embellishments. We'll worry about that in a minute. So let's start with, indeed, e to the x is n equals 0 to infinity of x to the n over n factorial. So this means that e to the negative x squared is this power series with x replaced by negative x squared. And it's that. So before we go and multiply by x, it's a good practice to always distribute exponents into the individual factors. So we never really want to write it like this. We need to write this as negative 1 to the n and then x to the 2n over n factorial. So this is what e to the negative x squared is. So now if we simply multiply by x, and you can see we're just incrementally building the original function that we seek. Well, that's just like multiplying this power series by x. Of course, we can multiply by x on the outside. Let's do that just for a moment so that when you're reading this later, you can see what our thought process was. But of course, that x distributes all the way in, and it really just means that this is x to the 2n plus 1 instead of x to the 2n. So there we are. Behold the Maclaurin series for x e to the negative x squared. Okay, so for this particular function, we need to recognize what form we can use to kind of bridge it over into the universe of power series. And this looks a lot like the form of the geometric series, which is 1 over 1 minus x, because we know that 1 over 1 minus x is equal to that. So all we have to do is figure out what specific embellishments have been applied to this function, and then we can commute it over to its power series version. So this time we should work directly with the function rather than what we did with the last example, which is we started with the form e to the x and we just kept, adding the embellishments until we got what we wanted. Here we should try to make this look like 1 over 1 minus x. So one thing we'd really like is that to be a 1. So why don't we just factor 1/3 out of this entire expression? And we get something like this. For that matter, we also want a 1 in the numerator. So I suppose we could have just factored x over 3 out from the start. And let's write this as minus negative 2/3 x cubed. Okay, so we're ready to bridge this thing over because this is in the form of 1 over 1 minus stuff. So that stuff is right here. So 1 over 1 minus stuff is the sum of stuff to the n. So we just have to clean this up. All right, well that's going to be negative 1 to the n, and then 2 to the n, x to the 3n. This is over 3 to the n. So our last move is just to bring the x over 3 into the sigma. So we're going to get 2 to the n, x to the 3n plus 1 over 3 to the n plus 1. And there's our final answer. Okay, so let's start by acknowledging an incorrect approach here. You may think, well, we have a sine of x, and we know sine of x is equal to this. So that means that sine squared of x must be, well, the square of that, which is true. The problem is that squaring a series is actually an infinite foiling job. And that's definitely not what we want to be doing right here. So you cannot just say, oh, let's square every term. That is definitely not correct. So remember, sine of x is really these terms here, right? And so if you squared that, you'd be having to do this really infinite FOIL situation. That is definitely not the approach we want to take. So for this one, we're going to actually just apply an identity right away. So let's recall that sine squared of x is 1/2 of 1 minus cosine of 2x. That's an identity that you used all the time in calculus in order to integrate even powers of sine. So specifically, it's probably more convenient to write it like this for our purposes today. This means that f of x is really x over 2 minus x over 2 cosine of 2x. And we can easily find the power series for x over 2 cosine of 2x. So we know that cosine of x is given by this power series. Okay, so therefore, x over 2 cosine of 2x is x over 2 times this series with x replaced by 2x. So this would be, okay, well, we've got a lot going on here. This would be 2 to the 2n minus 1, because the 2n distributes, but we're also dividing by this 2. And then x to the 2n plus 1, and that's all over 2n factorial. Okay, so that's what x over 2 times cosine of 2x is. But remember, our f of x is x over 2 minus this thing. All right, something very interesting happens here. Note that the first term of this particular series, that is, if we let n equal 0, we actually get, naturally, x over 2 coming out of that. And that would leave the rest of the series, which starts at 1. So you can see that these two terms are going to cancel, and we just get negative of this series. Okay, and that's pretty good, but we can do one more cool thing, and that's simply recognize that having a negative of an alternating series is a little bit silly. Why don't we just offset the power of -1? And that is the Maclaurin series for x sine squared x. So in order to use a power series to solve a differential equation, we need to be able to carry out a few new maneuvers. One of these is called shifting the index of summation. So what the heck is that? Well, let's look at an example. Let's say we have this power series right here. What we want to do is shift the index of summation, so the power series involves just x to the k. Right now, it's x to the n minus 2. So what we'd like is x to the k. But this means that all the n's in the series are going to be instead some version of k, including the first index of the series. So the way we look at this is we see that x to the n minus 2, what we want is we want this to be k. So we're going to let k equal n minus 2. And it may help to write n as k plus 2 if needed. So that means that our series, which is currently in n, can be written in terms of k. So n is k plus 2. So this is going to be 3 times k plus 2 plus 1, c sub k plus 2, and then x to the k as desired. Where does the series start? Well, when n is equal to 1, k is equal to -1. All right, so this is our new series. We can clean it up a little bit. Maybe write this as 3k plus 7. So this series is exactly the same series as the original one. Even though it has a different letter, you could even write this with an n again down here. This letter n or k, these are dummy variables, meaning they're variables that are part of the notation. So the n and the k do not exist externally from this series, unlike the x variable, which does. Let's verify that we get the first term equal in both cases. So when n is equal to 1 here, we're going to get the first term being 4c1 and then x to the -1. And when we write the first term of this series, when k is -1, we're going to get 7 minus 3, which is 4, -1 plus 2, which is 1, x to the -1. So indeed, this will generate the same terms as this will. All right, so this is a typical type of situation you'll encounter while solving a differential equation using a power series. So all we have to do right here is practice the technique that we're going to need at that later stage, which is writing this as a single power series involving simply x to the k. Okay, so the first thing to do is for each of the component series here, shift the index to involve x to the k. So for this particular series, we can see that we want k to equal n minus 2, or n to be k plus 2. So what's that going to give us? Well, n is k plus 2, so we're going to get k plus 2, and then n minus 1, which is k plus 1, and then c sub k plus 2, and then x to the k. And this series, we can see when n is equal to 2, k is equal to 0. For the other series, we want k to equal n plus 2. And it's okay to reuse the k here. This isn't a conflict in definition because these are internal to the little parts of the problem. So k is n plus 2, therefore n is k minus 2. And we're going to see that Cn is going to be c sub k minus 2, and x to the n plus 2 is x to the k, as desired. When n is equal to 0, we can see that k is equal to 2, and, of course, infinity up there. So where are we here? The problem says to actually write these as a single power series. So getting these both to x to the k was just the first step. The next step is to combine them to a single series. The problem is that they don't start at the same k value. So what you have to do is run off a set number of terms from any of the series that haven't caught up to the other one. So what I mean by that is this k equals 0 hasn't caught up to the k equal 2 one yet. So we need to run 2 terms off of this series. So by running off the 2 terms, that means plugging in k equals 0, which is going to give us 2 times 1 times c2 x to the 0, and then plugging in k equals 1, which is going to give us 3 times 2 times c3 x to the 1. And now we have all the other terms, which are 2 to infinity of this thing. And we're adding to that the other one. So now all the series, and here there are of course only 2, but they all start at the same index and they have the same power of k, which means finally we can sort of factor this sigma out of these 2 series and we'll have a single series. So where are we here? Well, let's clean this up a little bit. This is just 2c2 plus 6c3x plus k equals 2 to infinity of, all right, well, k plus 2, k plus 1, ck plus 2, and then plus ck minus 2, and x to the k. And sometimes something nice happens with this part, but in this particular situation, it doesn't seem like that's going to happen. So this is as good as it gets. All right, in the next section, we're going to be seeing how we can use a power series to solve a differential equation. But what we're going to do right here is assume that we have such a solution, and we're going to verify that it is indeed a solution by substituting this into the original differential equation. Now, in this particular case, this is a first-order linear differential equation, so we really do know how to solve this, using classic techniques. And moreover, you may even recognize this function here as simply y equals 1 over 1 plus x squared, which if you took its derivative and plugged y and y prime into all the right places in this differential equation, of course, this would work. So what we want to do here is pretend like this is not a differential equation we can solve any other way, and perhaps we don't recognize what function this represents, and see if this works, because this is going to be kind of what the situation looks like with harder problems. So yeah, let's take our y prime. So the 2n would come down, we'd get x to the 2n minus 1. Note that the first term of this series is actually 0. So this series ought to really start at n equals 1. And now we have both y and y prime. Let's go plug them in where they belong and see if we get 0. So, of course, we're going to work on the left-hand side of our differential equation. So we have this, which is equal to, well, let's insert y prime. That would be this particular series here. And we're adding to that 2x times y, which is this series. So we just need to do all the necessary algebra, including very likely shifting the index of summation, combining to a single sigma, and somehow it should become evident that this entire quantity is equal to 0. It's not obvious to me that that's the case yet, so let's play with this. Let's distribute the summation here into this binomial, so we're going to get 1 times this series plus x squared times that series. But I think it's a good idea to distribute the x squared into the series right away. So instead of this being 2n minus 1, the power will be 2n plus 1, because we multiplied x to the 2n minus 1 by x squared. And let's also distribute the 2x into this summation. So we're going to get a factor of 2, and then x to the 2n plus 1. Okay, so our job at this point is to combine these into a single sigma. Of course, our first step to that would be to shift the summation so these have the same power of x. Okay, well, these two series here have an x to the 2n plus 1, so why don't we make this first series the one that conforms to that? So what do we want? We want that to be 2n plus 1. Let's introduce a k here, so we really want the existing 2n minus 1 to equal 2k plus 1. Okay, so this tells us what? Solving for n, we're going to get, by adding 1 to both sides and dividing by 2, we're going to get n is equal to k plus 1. Or solving for k, we're going to get k is equal to n minus 1. So either form may be useful, depending on what we're going to do here. So we're going to replace all our n's with k plus 1. And that means that this power of x, by design, will be 2k plus 1. We also need to adjust the lower bound of the summation. So when n is equal to 1, k is equal to 0. All right. The other ones we can leave as n or switch over to k so that everything's consistent. I'll just switch everything to k at this point. But they have the right power of x. So we're not going to do anything else to those ones. All right, so the next thing we need to do is we need to run off the initial terms of 2 of these series so that they all start at the same k value, which is k equals 1 is what our target would be. So you always have to run off so that they all match whatever the highest initial k value is. So we'll have to run off a first term of the first series. So that would be k equaling 0. And we can see when k is equal to 0, we're going to get negative 2 times x. And then we'll just have the rest of the other terms, which are just k equals 1 to infinity of all of this stuff. Okay, the next series, we'll leave it alone because it already starts at k equals 1. And the last series, we need to run off a term of that one. So that's going to be positive 2x. Okay, so remember, we're hoping this comes out to 0. So we do get a little bit of cancellation right there. The good news is we can now write this as a single sigma because the index all starts at 1 and they have the same power of x. So we can write this as k equals 1 to infinity of, so we're factoring out kind of the sigma on the left and the x of the 2k plus 1 on the right here. So we're going to get this plus this plus this, and then that's x to the 2k plus 1. All right, I think we're going to get the cancellations we want because all we have to do is kind of distribute this guy, and we're going to get negative 1 to the k plus 1 times 2k plus negative 1 to the k plus 1 times 2 plus negative 1 to the k times 2k plus negative 1 to the k times 2, all times x to the 2k plus 1. All right, well, notice that this term and this term always have opposite signs, so those are going to cancel. And the same is true for this term and this term. That means that this entire bracketed expression here is going to be 0, which is perfect because we want this whole thing to end up being 0. If you want a more mechanical way of just convincing yourself that this quantity plus this quantity is equal to 0, well, just factor negative 1 to the k out. So we get negative 1 to the k, and then that would leave us with a negative m plus m, regardless of what m is. And you can obviously see this is going to equal 0. So that allows us to say this guy cancels out with this guy cancels out with this guy, and what are we left with? 0 times x to the 2k plus 1. Of course, that's just 0. And that's the right-hand side of our differential equation. So we verified it. Hooray!